Okay, can you hear me?
Yeah.
Good. So, thank you very much for having me here again this year. Last year, at the previous iteration of this workshop, I was presenting the automated 2D pre-processing pipeline in a software package called Warp that I wrote. Sorry. So there haven't been that many changes since then. Most of them have been only under the hood. I don't think many users noticed, except that hopefully their user experience got a bit more pleasant. But a few notable ones are more speed, especially if you have a multi-GPU setup. There is a REST API that lets you programmatically talk to Warp from anywhere outside. If you have a machine connected to the same network as Warp, you can set it up. So a different system can talk to Warp. I think this is also how Scipion intends to implement their Warp integration. And most importantly, you guys are now all getting those fancy new K3s. And if you got the GPU option, then your K3 server, which by the way runs Windows, can run Warp at about 300 non-super resolution 40-frame K3 movies per hour. But today is not going to be about this. I think this workshop this year is already trending more towards tilt series and tomography. And I hope I don't take too much away from the next session when I tell you that tomography is awesome. We should be doing it more. Now, my cat certainly agrees about that, and it really likes to chase flies. So it really wanted me to implement on-the-fly tilt series pre-processing in Warp. Now, when Warp came out, or actually even the latest version, in tilt series pre-processing mode, it looks like this. Most notably, it lacks all of the additional options that 2D data pre-processing has in Warp. So you can pretty much only estimate the CTF after manually importing pre-aligned tilt series from iMod. And that's it. Everything else related to tilt series in Warp has been delegated to purely offline tasks. So there is no way to do on-the-fly processing with that. And why is it so? So tilt series are a bit harder to do on the fly than 2D data because they have more ways in which they can fail. The most obvious one, since in on-the-fly processing you want to continuously be looking for new data somewhere, with tilt series it's really not obvious that the tilt series has even finished or has been aborted prematurely because serial-EM lost tracking or something. Tracking usually works, especially with Vim's latest scripts. It works quite well, but there are still a few edge cases where it fails. Sometimes it fails really hard, where you have to discard maybe half of an entire tilt series. And if you're implementing the new fast tilt series acquisition scheme, since you're not doing any tracking at all of your tilts are going to be quite a bit off. I mean, not as much off as if tracking failed with previous acquisition schemes, but everything's going to be a bit off. And a lot of the voxels inside of your tomograms are not going to be covered by all of the tilts. You would like to keep your field of view that is covered by all tilts in the tomogram as big as possible. And due to some technical reasons, you might get blank tilts. Those are obviously not going to be alignable. They're going to throw off serial-EM totally. No, iMod for the alignment. Sometimes some big, very dark object, either grid edge or huge ice crystal or ethane or whatever, comes into the field of view. That totally messes up everything. And especially if you're doing flipped lamella, at high tilts, you get very strong charging, which leads to a super strong anisotropic motion that you would most likely like to exclude from any kind of high resolution processing. So it's probably still okay to do just the initial tilt series alignment, including those frames. So this is what tilt series pre-processing in Warp looks in the next version. So this is still very much work in progress. So I haven't cleaned up the GUI as much as I have for the 2D case. So I have to actually split it down 2 columns on this slide so you can see something. So the first addition is Warp can now import tilt series information automatically from mdoc files that Serial-EM generates. And there are a few additional parameters that let you specify how to handle those failure modes that you have additionally for tilt series. Then pre-processing CTF is the same as before. It already worked. And then you can now align the tilt series on the fly. Now, this has been probably the main reason why this has been delayed for so long. Basically, I've been trying to come up with an idea to improve tilt series alignment significantly over what IMOD already offers. And I have not succeeded in that so far. And at some point, I decided just, well, IMOD does it quite well, so let's just integrate IMOD. But you will never see IMOD in Warp. It is integrated completely transparently. It does everything behind the scenes. And you just get to specify a few options. And then Warp just takes a pre-made text file with commands, modifies a few things, and sends them off to IMOD to execute them. And then once it gets the elements back from IMOD, you can reconstruct the tomograms. You can also deconvolve those reconstructed tomograms. You can also seamlessly generate reconstructions from all odd and all even tilts, which is what you need if you want to do deep learning based denoising, which I will talk about later. And so this align tilt series part is pretty much vanilla IMOD, but with a bit of a special sauce. So one part of the special sauce is you can use the same kind of model that Warp uses in 2D to pick particles and to mask out crap in the micrographs, to also mask out crap in the individual tilt images. So here in purple, you can see, in this case, I trained the masking on just 2 tilt images and then let it mask the rest of that tilt series. And if you do that, you can get rid of quite a bit of crap in this tomogram, which would have otherwise messed up your analysis. For example, template matching goes crazy when there are such high contrast objects. Now, it didn't catch all of those tiny blobs, basically because I was just too lazy to create training data that included all those tiny blobs, because you have to click a lot. But if you took the time, you could also get rid of the smaller things. And I already mentioned it can also automatically deconvolve the tomogram to boost the low resolution signal to get a look that is more like the volta faceplate. And if you reconstruct all the odd and even tilts and train a 3D denoiser on them, then you get an even nicer result than with the deconvolution. This is the denoised tomogram on the right. So where does this put Warp in the context of the current tomography, especially subtomogram averaging pipeline? Now there is this nice review from the Kudryashev lab that appeared earlier this year, where they list all of the different options and all the different steps that you currently have to take to get to a high resolution subtomogram average. Now, this is a lot. There is a great Russian word to describe that, which basically translates to clusterfuck. And to be fair, for 2D data processing, we have probably as many options as we have for tomography, but for 2D, the community has kind of agreed to focus on just a few packages. I mean, there is a reason why Rulion is only 1G away from a religion. So warp comes in here, and then takes you all the way through this without any interruptions, seamlessly, and then lets you reconstruct subtomograms that you can pipe into Rulion to do global alignments and classification. And then you can pipe Rulion's results into a new tool called M. If you've been following me on Twitter, then you probably already heard all about M. But just a few words. M is basically the opposite of warp. It lives on the other end of the pipeline. You know, it's like in Nintendo games, Mario and Wario, except calling it MARP probably would not have attracted that many users. And M does what I call multi-particle analysis. Basically, in single particle, the central assumption is you have one particle per image, and you analyze all of that in isolation. Basically, you assume that your particle exists by itself in a vacuum. Now, with multi-particle analysis, you acknowledge the fact that you usually image a whole big system of particles at the same time, embedded in the same layer of ice. And so this system has additional hyperparameters that M lets you fit simultaneously with particle poses, such as global shifts, local image or volume warping, stage angles, all possible CTF parameters, beam tilt, pixel size, and maybe I forgot something. And it lets you do this for both 2D and tilt series data. It's basically data type agnostic. The code looks almost 100% the same between 2D and tilt series refinements in M. Now, a lot of these concepts are not new at all. In fact, Rulion has been doing its polishing for 2D data, which is conceptually very similar to this. And back in 2012, Alberto Bertisaghi published his constrained single particle tomography paper. Unfortunately, did not provide any implementation of that. But the most notable descendant of that concept right now is EM Clarity, which then does something similar to what M does for tilt series. And this is what M looks like. Pretty much the same look and feel as warp, except doesn't have that many GUI elements yet. You see it can refine epiferritin. This is still very much in the making. The 106 release of warp included the first public, probably not even alpha version of M. It had quite a few bugs, but if you want to go back to 106 and try it, it's already usable. I took it out in 107 because we want to publish some preprints about it soon. And so, since this is data type agnostic, I was very curious whether 2D data refinement does better or worse than tilt series refinement. So I asked our facility manager, Christian, who's also here today, to collect two nice small data sets of our Lord and Savior, the epiferritin, and process them independently with warp line, and in the case of tilt series also with M, and got these two results. They both have the same nominal resolution, but you can see there is a bit of a difference in actual map quality. So just a quick show of hands, who thinks that the one on the left is tilt series? No one? The one on the right, just as a control? Okay, well, I guess that was a bit rigged in favor of tilt series. So indeed, tilt series in this case provided a better result than 2D data. Take this with a pinch of salt because the 2D data has only been processed with warp and line. Maybe there is still a bit more resolution to be gotten by processing it in M. But in general, I think we're now at a point where for the same sample and the same amount of data, we can get the same or maybe even better resolution with tilt series. So if you want to do tomography on in vitro samples, you can fully expect to get to at least the same resolution as you would with 2D if you took all the time to collect as much data. Right now it still takes way more time. Now I showed you some apoprotein. Now it's time to show you some ribosomes, since this is about methods. So I'm super excited about this ribosome. It's a bacterial 70S ribosome reconstructed from 24,000 tilt series particles. And it got to 3.7 angstrom, so basically a resolution where you can already start building a model. Now, you might be wondering, why am I excited about a 3.7 angstrom ribosome? I mean, this hasn't been excited for the past 10 years, or maybe even longer. So the reason I'm excited about this is because this is what the raw data look like. It's actual in situ. We imaged those ribosomes directly inside bacterial cells, unperturbed, except maybe for the outer membrane, outer surface of the bacteria. So this thing has everything in it that life needs to live. It's a crowded environment, about 150 nanometers thick. And it gets you to a resolution where you can see, where you can start to see the antibiotic that those ribosomes were stalled with inside that organism. You can also most likely see a magnesium ion next to it. So the resolution is really already there to do high-resolution studies in situ. Now, I know this is not a fit lamella. There are certainly a few more things that are a bit more difficult about fit lamella, but I'm very hopeful that we could soon achieve similar results in fibbed eukaryotic lamella. So, to finish it off, I am aware that warp and all the other tools running on Windows does not make everyone happy. So I just want to give you more reasons to invest into this whole ecosystem. Now, of course, warp does on-the-fly 2D and tilt series processing. There are different deep learning models that are fully transparently integrated inside warp. I think it's a much better experience than all the standalone tools that are coming out right now. It provides you with 2D and 3D denoising. The 2D denoising you can do fully on the fly. The 3D denoising you have to do offline because it takes a bit longer. You have seamless integration with Reliant, both input and output from Reliant. You have now M, which lets you take your tilt series data to never before seen resolutions. And last but not least, Membranorama is also a tool in this ecosystem that I wrote a few years ago to help people visualize and make sense of membrane proteins directly in the context of membranes, because usually if you try to look at membranes and tomograms, they're not going to be oriented nicely in the XY plane. So this tool lets you basically unwrap those membranes. And coming hopefully soon, 3D PCA and deep learning-based autoencoders to help you make sense of all the heterogeneity, especially in situ. With this, I would like to thank my boss, Patrick Kramer, who has shown me almost unconditional love and support. Christian Dienemann, who is here today, collected the 2 apoferritin datasets, and Liang and Julia in Heidelberg are the collaborators for the bacterial in situ. You can find most of these things online, either on the WARP webpage or in my GitHub repository, and if you want all of the latest updates, just follow me on Twitter. And with this, I will be happy to take your questions over a coffee, because I think the coffee break should start now.
Thank you very much for an impressive talk. Any questions? Bruno?
It's indeed very impressive. I was wondering how the tilts data were collected. Design scheme or which way?
Well, since they were collected in Heidelberg by the Dutch superstar drummer, who also moonlights as the facility manager there, I would assume that those were Hagen schemes. Yes. I'm very much waiting on the EMBL folks to release their raw data for this comparative study that they did recently for the different tilt series acquisition schemes. But yeah, Dell symmetric is the way to go right now. Yeah.
You showed that you can remove the crap from your list. Can you also use that as a pseudo-fiducial marker?
The way Eman is doing it, no. I mean, ideally you would not have any of that crap anyway. And all the reference-based alignments later achieve much higher resolution than you could ever achieve with crap-based alignments. And patch tracking works for pretty much all of those data.
Just want to add, if there's stuff on there that you don't want, like crap or stuff, you typically see it move anyway during the tilt series. It's typically then on top or the bottom, and then as you tilt and you illuminate, you just see these things move. They're like the least stable part of all the